With Eduardo, or with who? With Pietro? Yes. Yes.
I don't know.
At lunchtime.
think we can start. There are two contributed talk on the topic of radio at large. So the first one is by Zsofi Igo, Global Energetics and Feedback, as taught by AGN Incidence.
So yeah, hi everyone. I'm Zsofi Igo. I'm a PhD student here at MPE, finishing this year. I'm working with a lot of people also mentioned on this slide. I'm a PhD student of Andrea Merloni. And today I'm going to be presenting to you a bit of my PhD work, mainly focused on massive galaxies, so AGN feedback and accretion in massive galaxies. But at the end of the talk, I'm going to show you one slide teaser of what I'm working on now, of propagating this knowledge of accretion and feedback also to the low mass regime in these intermediate mass black holes as probed by Rosetta, so X-ray detected AGN in dwarf galaxies. But so the title of this talk is Global Energetics and Feedback as probed by AGN incidences. And to introduce what I mean by this, what are AGN incidences? I've taken the liberty to steal Antonis's slides, which I think really nicely explains how this how AGN kind of populate galaxies or found are in the centers of galaxies, and then these galaxies populate the cosmic web throughout the universe. And schematically, how this can be kind of shown more simplistically is here I'm showing a sample of galaxies. And you see two of them have these radio jets. So what I mean by the radio AGN incidence is this fraction of galaxies hosting radio AGN. In this case, you see 2 out of 7. And so why are they important? Well, we've been talking throughout this week, kind of these two schools of thought about either in detailed in situ measurements of these feedback mechanisms of looking at, deep observations of a single source and getting all the details of all the mechanisms and all the different scales versus kind of these large scale population studies to really get an understanding of the global energetics of how these AGN kind of feedback their energy to their host galaxies and why this is important. So I'm going to be motivating like the latter part, this population studies to get more understanding of this. And mainly because, these kind of population studies of AGN incidences, it can tell us about the triggering, the fueling, the jet powering mechanisms of AGN with different properties. So those that live in galaxies of different masses, live in different environments, have different jet powers, have different jet morphologies, as we saw from the NICE review talks this morning. There's a wide variety of physics going on here. Also, we can use these large-scale statistical studies to understand small-scale accretion physics. And thirdly, we can get an understanding of the distribution of power and AGN feedback, because we're essentially building luminosity functions through these sources, through these studies. So I've kind of split this up into two boxes. These are kind of two of my projects that I've been working on, and I'm going to introduce to you the first project and mainly focus on this third bullet point, which is part of the newest paper. It's coming soon to arXiv if you're interested, about this distribution of power, this global energetics. So to give a bit of a background on the data and the context, so this work was entitled The Incidence of Radio and X-ray AGN and the Disk Jet Connection. And in this work, we created a complete and volume limited sample of LOFAR radio AGN and Rosetta EFET's X-ray AGN. And we see this sky plot here showing the distribution of sources in this equatorial field of also Rosetta, which is shown in blue, EFET's field, the pilot survey of the all-sky surveys. Also, we identified host galaxies in the legacy survey, this photometric survey, legacy survey DR9, and also importantly, this gamma 09 survey. This is a spectroscopic parent galaxy sample, so with spectroscopic redshifts, and also host properties calculated via SED fitting, so stellar masses and star formation rates. So we built really a well-characterized, complete volume-limited sample for this investigation. As I said, I'm dealing with massive galaxies, so this is greater than around 10.6 in log stellar mass, all the way up to 12 in log stellar mass at low redshift, so less than 0.4. And we're really dealing with quite large samples, so around 700 radio AGN and around 300 X-ray AGN. And actually the X-ray results, there are many, but I'm not going to present them in this talk, given that it's a radio session, but ask me later if you're interested. Also, there's many experts in the room who've done many advancing works on this X-ray AGN incident. We can have a nice chat about that later. So the goal of this work was really to study the AGN incidence, so the fraction of galaxies hosting AGN, as a function of these mass scale power indicators. And what I mean by mass scale power indicator is basically a luminosity scaled by mass, so divided by the mass of the galaxy that these AGN live in. And I'm going to parameterize this as this lambda jet parameter, and I'll explain that on the next slide. But for example, we can ask ourselves the question, what is the fraction of gamma 09 galaxies, so the ones that live in that purple region there on the sky plot, hosting radio AGN as a function of this radioluminosity over stellar mass in different stellar mass bins. And I show you a bit the distribution on this bottom right panel of the redshift versus stellar mass of my radio AGN population. You see in different colors, they're split into the different stellar mass bins, and in the two redshift bins, they're split vertically. Okay, so as I mentioned, we're interested to study the AGN incidence as a function of mass scale power indicators. What do I mean by this? This lambda jet parameter, the specific black hole kinetic power, which I'm gonna write as this jet power divided by the Eddington luminosity. So this is a luminosity converted to a jet power with the scaling relations we saw from Beatrice nicely in the introduction talks, and then the stellar mass converted to a black hole mass with some assumptions, and then converted then to an Eddington luminosity. So this gives our mass scale power indicator in terms of the radio. If you want to make an analogy to the X-rays, this is kind of like the lambda Eddington, so the Eddington ratio. We define similarly as the bolometric luminosity over the Eddington luminosity. Okay, but we're not only interested in looking at this as a function of mass scale power indicators, but also as a function of radio morphology. Because we know that radio AGN can come in a variety of morphologies, such as these compact or complex cases. And we're asking ourselves, does this have an impact on the way these jets are powered in these systems? Or can we learn some new physics about why they are like this, or reversibly, how their shape impacts the way that they feed back energy to their host environment? And an important point to note here is that these complex sources, they're often greater they're greater than 40 kiloparsec in physical size. So they're larger than these typical galaxy scales, which you see very well in these FR2 cases here, that the galaxy is this black dot here, and the FR2, this double-lobed galaxy, is stretching way, way further than the galaxy scales. So take a note of this and when you're thinking of where the energy is being deposited in these systems. Okay, so moving on to how I actually calculate this incidence. Well, I split, first of all, in this redshift stellar mass plane, as I showed on the first slides. And within each of these kind of squares, I can split up my sources within a third parameter of choice. So this is going to be my lambda jet parameter, this mass scale power indicator. And then within each of these purple bins, I can calculate the fraction of radio AGN over the fraction of parent galaxies in that sample. And that will be my AGN incidence. So let's look at the results. But before I show you that, this is another nice field. So from the LOFAR EFETS field, this equatorial field, and you can see exactly the variety of sources that are present here. For example, this one is a giant radio galaxy. There's a lot of double sources. So these, these FR2 galaxies, there's a lot of points, complex radio AGN. So there's a wide variety of sources here. And what we can learn from this, if we look here, this is the incidence of compact radio AGN as a function of mass scaled jet power. So to walk you through this graph, I'm showing on the y-axis the fraction of galaxies hosting compact radio AGN. On the x-axis is the lambda jet parameter. So it's increasing jet power to the right. And also in the colors, we see increasing stellar mass from yellow to crimson. And what you immediately notice is that higher mass galaxies are more likely to host compact radio AGN. So somehow there's kind of a mass dependence of this jet powering mechanism coming in here. And not only this, but actually they're very nicely described by these power law distributions. So this shows that there's a broad distribution of these lambda jet parameters that it's not only the high mass galaxies hosting high power jets and vice versa, not only the low mass galaxies hosting low power jets. In fact, they host them in relatively equal fractions. This is also maybe a misconception for those maybe not working in radio or working more with kind of pointed observations of the most powerful, fantastic sources. Okay, so this is only the compact case. Well, what about now the complex radio AGN? So actually, one of the most important findings of this work was that radiomorphology affects the incidence of radio AGN. And as I showed on the previous slide, this compact only case shows the steep distribution of the fraction of galaxies hosting radio AGN as a function of this lambda jet parameter, and a relatively small mass dependence, but still non-negligible. I talk about this small mass dependence as something interesting because in the X-rays, you actually don't see that much of a mass dependence. In the X-rays, they populate kind of regardless of their mass. And the X-ray AGN populate their galaxies kind of in a mass independent way, which is interestingly contradicting to this radio perspective. But getting back to here, so as we saw, the compact only cases, they show the steep distribution with smaller mass dependence, and the complex only radio AGN show a much flatter distribution and a much larger mass dependence. So there's a difference here in the way that these compact and complex radio AGN populate their galaxies, and we'll see later on of how this directly impacts on how this energy from these systems gets fed back into the host galaxy and into the host halo. And I wanted to introduce this part with this nice image here of this AGN feedback in a galaxy cluster, where we talked about, how do we look for evidence of AGN feedback in the system? What is the direct evidences of this AGN feedback? And I think, these are some of the clearest example of jetted feedback in galaxy clusters or in AGN, where these jets kind of carve out cavities, and we see like this depleted X-ray emission in these cavities here. So I think this is a really interesting way to look for the impacts that these radio AGN can have on the galaxies. Okay, so the first thing we can do to understand a bit more about this global energetics is to go from our radio AGN incidence to the radial luminosity functions, because we know that if we can convolve the radio AGN incidence, so the fraction of galaxies hosting radio AGN, given we know their stellar mass and their radio power, with the stellar mass function, so how the galaxies of different masses populate the universe, we can actually recover the radioluminosity function. And we actually recover it that's in an agreement with the literature. So this makes us confident that our incidence distributions that we derive are reliable, and we can use them to later infer kind of global energetic statements about this sample of objects and about radio AGN in the local universe in general. And why it's interesting, I've put it on this slide because it's the first time we actually decompose the radioluminosity function in stellar mass and radiomorphology components. And I think this was really useful for disentangling degeneracies in AGN feedback simulations. It's why I wrote here that not AGN feedback, but audience feedback is wanted with this work, because I'm really curious how this can guide simulations to better kind of fine-tune their inputs to simulations and not just reproduce the radioluminosity function and say, woohoo, we got it, but actually get the mass dependence and the relative proportions of different types of radio AGN correct in their simulations. Okay, so again, the main point I want you to take home from this presentation is that AGN incidence studies, so population studies, are very, very powerful, because we basically know what galaxies host radio AGN, what masses these galaxies have, and what jet powers these radio AGN in these galaxies have. So when you combine these three metrics, you can derive the average jet power of massive galaxies as a function of mass and radiomorphology, which is what I'm showing on this slide. And we can use that to get an understanding of the global energy budget of radio AGN kinetic feedback in the local universe. So if we go into more detail about how that plot is created on the right, how do I actually go about calculating this average jet power? Well, as I showed you, we can model these incidence functions, so we can interpolate within the mass bins to get a continuous function of stellar mass. We can extrapolate to the low and high end of the low and high jet powers to cover the whole parameter space, and then integrate underneath these curves. So find the expectation value of the lambda jet, so the average specific black hole kinetic power, and convert that back at a given stellar mass to the average jet power. Note that already this takes into account the duty cycle because I'm using the incidence, right? I'm already taking into account how often these AGN events occur. So when you do that, you get this plot. So on the y-axis, I'm showing you the average jet power mass of galaxies at this low redshift, so less than 0.4, as a function of stellar mass. In the different colors, we have the light blue is the compact only contribution, and the dark blue is the complex only contribution. And the sum is shown in this black dashed region. And you can also convert to on the other y-axis, you have the jetted energy. So this is converting the power to an energy multiplying by the look back time in the redshift bin. And what you can see as the results of this work is that actually the compact, so the ones that are small, less than 40 kiloparsec in size, these compact radio AGN dominate the feedback budget over a very large mass range up to around 11.5. And it's only after this range, so greater than 11.5, that the complex radio AGN dominate. And in fact, there's not so many galaxies there at this point. The stellar mass function steeply declines at these masses. So this is also a kind of misconception that we have, is that it's not always the most powerful, beautiful FR2 galaxies that are doing most of the damage and that are often the targets of these pointed observations. But actually, it's the small little compact sources that are, chipping away at the galaxies and cumulatively doing most of the damage in this feedback budget. And actually, this is able to be found because of also LOFAR and also going to these wide field, low sensitivity surveys. Sorry, wide field, high sensitivity surveys. Okay, and in comparison, I want to point out, now highlighted in yellow, this dashed dot purple line, which is a measure of the kind of radiative feedback. So it's 0.5% of the average AGN radiative energy output. We talked about this value from the Di Matteo paper. It's kind of like the canonical fraction of the the radiative energy that can couple to the environment, to the interstellar medium with these multi-phase winds. And if we look at this graph, we see that the jet kinetic feedback dominates over radiative feedback in the local universe, especially as you get to higher mass galaxies. And you may not be super surprised by this point. You say, okay, I already know this. But I will show you later of how we can convert this average jet power into more tangible metrics and to show you how that can be used to understand really physically what is happening in the galaxy and halo scales. But before that, I also want to get some more audience feedback on this because I wondered how can this observationally defined average jet power be useful to compare to simulations? And I really tried my very best to have a complete sample with all the variables controlled, very well-known galaxy sample, very well controlling for all the parts. And I wondered if this can actually help to, again, put more inputs in simulations to guide them to make better physical assumptions in their work. Okay, so moving on to how to convert this to a more physical metric to understand how they can impact their galaxies and halos. I'm gonna talk about 2 points. So the first point is this disruptive feedback. What I mean by disruptive feedback is the ability of these jets to kind of push out gas in their galaxies, so kinematically disrupt the gas in their galaxies. And how I parameterize this is I convert the average, so I compare the average jet kinetic energy. So remember, I converted from the average jet power with the look back time in the redshift bin, go from power to energy, to the binding energy of the galaxies. This is what I'm showing on the y-axis on this plot. And so highlighted in yellow is this equivalence, so where the jet kinetic energy equals the galactic binding energy. And what you already see is that the compact radio AGN provide only around 20 to 80% of the galaxy's binding energy across the mass range, but the complex radio AGN actually reach above the 100% line for the most massive galaxy. However, there's a caveat here of, again, what scales at which this energy is released, right? Because if I show you this very beautiful kind of canonical radio galaxy, this 10A, you see very well here that the radio jets reach way past the galaxy scales. So maybe looking at this disruptive feedback on galaxy scales is not the best metric to look at. Okay, so then let's look at it in the halo regime, so the larger scale regime. So I'm doing the same thing in this plot, except comparing it now, the average jet kinetic energy to the binding energy of the halo. And highlighting again in yellow, this equivalence between the jet kinetic energy and the halo binding energy. And now you see something much more different, right? But let's go through also the scales which are probed in this graph. So here we're going on the x-axis, we have now halo mass. And we're going through systems of isolated galaxies, which have halo masses between 12 and 13. Then groups of galaxies between 13 and 14, and all the way to clusters of galaxies between greater than 14 in log halo mass, sorry. And so what you really see here is that both compact and complex radio AGN do not have enough energy to unbind their whole entire halos. And this is kind of reassuring because neither in observations nor in simulations do we see radio AGN destroying everything. So great. But then you may ask, okay, again, so why should we care about radio AGN as a feedback mechanism? And this is where I'm coming to the second part of why they're important. Because we can also look at them as a kind of preventative feedback agent. We not only know that radio AGN can like push out the gas, kinematically disrupt the gas, but they can also heat the gas. So by heating the gas, they can prevent the gas from cooling and then forming stars. So this directly has a kind of negative feedback effect on the galaxy or halo components. And so we can convert our halo masses to get an understanding of what bolometric luminosity these halos have, to get an understanding of their cooling luminosity. So we see here the scaling from Lovisari 2021, basically showing that more massive dark matter halos have hotter gas and therefore higher luminosity. And so we can use these relations to reformat our plot here and divide now the average jet kinetic heating energy compared to the thermal cooling energy to kind of understand the thermodynamical balance in these systems. Again, highlighting in yellow this equivalence point. And what you see is that in galaxy and small group regimes, the kinetic energy from radio AGN jets can globally impact the whole entire halo. You see that they're around 1 or even greater than the 100% line. But in the large group and cluster regime, the jetted energy is only around 1 to 10% of the thermal cooling energy. So in fact, you see that there's no global impact as the jet kinetic energy is just too low. However, if we compare these sizes of these jets to the physical scale of the halo, so this is parameterized now by this R500 metric, 500 times the Fourier radius. Sorry, no, yeah. 500 times the critical density of the universe. So if we plot the observed sources here, what we see is actually as a function of halo mass again in the cluster regime that the R jets, so the physical sizes of these jets, reach only 2 to 10% of this R500 value. And so it makes sense that these jets cannot exert a global impact because the halos are simply too large compared to the size of the jets. However, again, we can make a little thought experiment to see even if the jets are not large enough to impact the whole halo, are they large enough to impact kind of the local scales of this heating and cooling balance? And so what we did to kind of test this is to model the distribution of the luminosity, the cooling luminosity in the halo gas as a beta profile, commonly done for halos. So this defines how this luminosity is distributed as a function of radius. And then we integrate starting from center out all the way up till this value until this integrated surface brightness equals the average jet power in that mass bin. So basically this is kind of testing the equivalence radius, so where the heating is equal to the cooling as a function of radius. And this is what I'm showing on these lines here, which have different beta profile and so beta values and core radii. So different shapes of how this luminosity is distributed, the cooling luminosity. And what you note here is that most of the observed radio jet sizes, if we just look at this red line, which is, let's say, the most canonical profile of this beta profile, all of these observed radio AGN kind of lie or cluster just underneath this curve. In fact, this is a kind of necessity of this assumption, right? If you're integrating from the center out, you need the energy of the jet to be within the volume that you're integrating in and to find this equivalent. But what it's showing is that this means that they have a local ability to impact the heating and cooling balance in these halos. And this is important because we see that they can actually have an impact or have an effect to offset the cooling flows, even in the largest clusters, where they cannot do a global impact, but they can be important to local thermodynamical balance. So I want to finish here with the summary of this part, where I showed you that the low-for-effect survey is a really powerful value-added survey that I've created and is also public to use. So if you're interested in nice radio, X-ray, optical data, reach out to me. There's also a lot more projects to do on this work. But I've really shown you that through radio AGN incidence studies, so these population studies, we can get a really good understanding of the distribution of how this energy is fed back into the galaxy for different masses, different radio morphologies, different environments. But that radio AGN cannot fully unbind their host galaxies and host halos, but that they can have an important global and local thermodynamic heating and cooling balance. And before I end, as I mentioned, I wanted to show you a bit about the low mass regime. I just want to show you one slide of what I'm working on now, which is combining the legacy survey DR10 and the IRIS-ZETA deepest all-sky survey, so IRAS-5 as we call it, to map out kind of the largest sample of X-ray detected intermediate mass black holes at low redshift. And I'm just showing some cutouts here of what kind of sources I'm detecting. Don't take them as face value because they're not correctly scaled yet. But I just want to show you kind of the things, the nice, like the breadth of sources that we can get with this study, because this is kind of the first time we've had a really deep X-ray survey to detect these objects. So exciting things to come. And if you're interested about this work, also talk to me a bit more, because I have more things to say. But yes, thank you very much.
Professor time, Benny.
Hi. If I recall correctly, gamma also has morphological information. You look into
Of the environment or the galaxy itself?
galaxies themselves.
Yeah, so I'm not sure actually. I didn't look into that in detail, but probably there is. I would guess there is. That would be interesting in terms of like looking at maybe barred galaxies or these kind of.
Even just ellipticals versus, dominated.
Actually, I didn't look at them, but I looked at maybe the cutouts of what they look like in the optical. So, but yeah, it would be also interesting to look at the morphology of the galaxies.
Can I ask a little bit about the details when you're talking about the energy coming from the AGN that in especially galaxy clusters, you just have, how do you calculate it? There may be multiple energy activities, you just sum them up, is that correct?
So I didn't understand the question.
In galaxy clusters, which is how many galaxies, there possibly have multiple AGN activities. That's correct, right?
Yes.
The energy is just you sum them up. Right.
Yeah, well, in the radio, it's what Beatrice and Francesco were saying, we have kind of an integrated over the lifetime of the source, this radioluminosity, and we sum the different components that can come from this AGN. Well, of course, we have to be very careful of not putting in, if you have a cluster, you have maybe 2 radio AGN in that same cluster.
Yes.
And yes, I think we have controlled for that in this experiment because I've visually inspected all the sources. So I've kind of looked at where the radio AGN the radio emission is coming from and allocating that to a host galaxy. But it's a very important effect in per se.
So it's only from the host central galaxy.
Yeah. So we also did
Also satellite galaxies.
Yeah. So most of actually like the vast majority, 80–90% of these sources are centrals given the gamma environmental data. So the gamma data has this kind of information of where these sources lie and whether they are the BCG or not. And the large majority of these sources, 80–90%, are the central galaxy. But this is a really good point, and I think it's not really well characterized yet, of the radio AGN and satellites and centrals, because they have vastly different properties in terms of maybe the stripping or other jet powering mechanisms, given the gas distributions at those scales.
Thanks, Zsofi, for the presentation and the huge amount of work. And so I have a question, is for the very beginning of the presentation. So how did you classify AGN as AGN and then to derive the fraction compared to the galaxy sample? And then maybe a question on the last part. So are you selecting dwarf AGN in dwarf galaxies or intermediate mass black hole for the last slide that you showed?
Yeah, so, okay, I tend to use the word intermediate mass black hole when I don't have enough time to explain what I mean by AGN in dwarf galaxies. But so usually intermediate mass black holes are tending to be defined as less than 10 to the 6 or 10 to the 5 in black hole masses. And I'm looking at a bit larger than that. So that's why I say dwarf galaxies, because usually dwarf galaxies are defined as stellar masses less than 10 to the 9.5. So it's maybe a bit larger than the traditional intermediate mass black hole regime. And that's why I would more like to say AGN in dwarf galaxies. But then someone may ask, maybe it's not maybe an AGN because it's a massive black hole. So there's all these different terminologies here. And in terms of the AGN, I brought up this slide. It's just a comparison of the radioluminosity versus the star formation rate. So you can see that the sources that may be dominated by star formation rate, they lie maybe in this star formation sequence, main sequence. And we take like 3 sigma above this curve. So the radio AGN is, so radio emission is much more dominant than what's expected from star formation at that given star formation rate. And those define our radio AGN sample. Also, we visually inspected them. So if we see kind of weird things going on, we look more into detail.
Yeah, just to make sure I follow what you've done. When you're plotting as a function of halo mass, you still, as you just said, right, mostly at the central. Not want for the whole budget also add some contribution from all members? Would that make a difference?
Yeah, but often we don't have information about all the members. And yeah, as I said, so the gamma has this information about whether it's a BCG or not. And the distance from the BCG. And I think, I mean, that's something I would be loving to work on after my PhD, to look at more the environmental part of this radio AGN triggering, because I think it's really interesting. And there's a lot of work now, also Mayoket did the reviews that you were citing, that find a lot of interesting things about the differences between radio AGN and maybe more isolated environments or more dense environments, how that impacts also firstly the radio emission, but also that the fueling of the jets and the impacts on the environment. I think that's really important to study.
We have one question, very quick, very fast.
I think it's quick. So I wonder what are the prospects for extending the incidences to higher redshift or something. You have thought about galaxy samples available for that, or radio requirement, radio sensitivity requirements as well?
I think the limiting factor for me was mainly the parent sample of getting the spectroscopic redshifts. So I can do it maybe with photometric redshifts, or also for this kind of work, you need a very well understanding of the stellar masses, the star formation rates, to then clean contaminants. In the radio, there's also a lot of contaminants in the star forming galaxies, as I showed on the extra slides before. So yeah, it's not the limitation in the radio per se, it's more the multi-value, multi-wavelengths.
The catalogs become very incomplete, I think.
Yeah, so also knowledge of the environment, like.
Okay. Thanks again.